In this video we will be looking at what's called Euler's Totient number. Okay, I'll explain very shortly what this number is all about. Now, maybe you watched the previous video. In that video we actually counted the number of divisors of a certain number, natural number n. Okay, now what we are going to do is we're going to take an n that's a natural number that's not zero. Okay, and we are going to count the number of numbers k, so the number of numbers k that are in between 1 and n, okay, such that the greatest common divisor between k and n is 1. Okay, so now k and n have no common factor, so it's kind of the opposite that as to what we discussed in that video that I just mentioned. So we want k and n to be relatively prime. Okay, the number of numbers k for which that are in between 1 and n, so that the GCD between k and n is 1, is called Euler's Totient number for n, and is typically denoted by phi of n. Okay, now, so maybe the theorems were proven to you at school, or you saw proofs of various things online, and most of the time a statement is given to us and then somebody goes ahead and does the proof. All is nice and smooth, and everything seems to be very simple. Actually, most of the time that's not how things happen in real life. Okay, most of the time, in order for people to come up with proofs, they go through examples, they try to figure things out, they try to get an understanding of, let's call it, the neighborhood of that problem, what's happening. Okay, and then eventually they figure out more and more and more, and hopefully they solve the problem. Okay, now one very important aspect towards us learning more about the problem is looking at some examples. Okay, so that's exactly what I'm going to do here. I'm going to look at some examples first and see what happens. Okay, so in here I wrote numbers from 1 to 12, so we're going to be looking at n is equal to 12. Okay, and so 12 is the number that we are looking at, so 12 is our n. So this is our n for now. Okay, so 12 is 2 to the power of 2 times 3, right? So 12 contains 2's and 3's. Okay, so let's see what relatively prime numbers with 12 we have in between 1 and 12. So 1 is good, 2 contains a 2, 3 contains a 3, 4 contains a 2, 5 is good, it's a prime number, 6 contains a 2, 7 is prime, all is good with it, 8 contains a 2, 9 contains a 3, 10 contains a 2, 11 is good. Okay, do we see anything in here? Well, it's one example. It's pretty much, it's very hard to say, oh, I see something and that's what's going to happen always. Okay, still what I see is, okay, maybe 5 and 7 are so close to each other, and there is a 6 in between. 6 happens to be a divisor of 12. I don't know, maybe there's something going on in here, maybe there's just pure speculation. So let's look at another example. So on this row, I wrote all numbers from 1 to 18. Okay, so our n now is 18. Okay, again, 18 now is what? 2 times 3 to the power of 2. So 18 contains 2's and 3's. All right, so 1 is good, relatively prime. 2 contains a 2, not good. 3 contains a 3. 4 contains a 2. 5 is prime, so that's good. 6 contains a 2. 7 is prime, so that's good. 8 contains a 2. 9 contains a 3. 10 contains a 2. 11 is prime, all is good with it. 12 contains a 2. 13 is prime. 14 contains a 2. 15 contains a 3. 16 contains a 2. 17 is prime, all is good with it. All right. Now, do we see anything else going on in here? Well, again, we only have 2 examples. Kind of hard to tell. Still, if I am to see something, okay, well, we have the exact same thing with a 6 here. We have the 12, okay, in between these 2 numbers. So, okay, so now things become a little bit more interesting, because I see that whatever happens in between 1 and 6 happens in between 7 and 12. I mean, look at the pattern, not the numbers themselves, and happens in between 13 and 18. So maybe there's something going on, okay? But again, 2 examples for sure have very little chance of actually telling you essential things. Okay, let's look at another one. Okay, let's say if n is 15, so I wrote here the numbers from 1 to 15. Now our n is 15, which is 3 times 5. Okay, so it contains a 3 and a 5, so 1 is relatively prime, 2 is okay, 3 no, contains a 3, 4 is good, all right, 5 contains a 5, 6 contains a 3, 7 is prime, so all is good with it, 8 is good, no 3, no 5. Okay, 9 contains a 3, 10 contains a 5, 11 is prime, so all is good with it, 12 contains a 3, 13 is prime, all is good with it, 14 contains no 3 and no 5. Okay, so this is sort of the picture we have for 15. Well, what's happening now, if we are to look at some divisors of 15, I don't know, let's see, we look at 5s. Okay, 5 and 10 and 15. Again, I'm just trying to see what's happening here. There's no guarantee that we come up with something. Well, actually, if we look at that, okay, so the pattern that seemed to have emerged before is kind of denied by this example, right? Look at what happens in between 1 and 5. It's clearly not what happens in between 6 and 10. It happens to be what happens in between 11 and 15, but so again, we were encouraged by the first two examples, and now we have a little bit of a setback here on the third example. So clearly, you know, our little speculations were not quite right. But what's happening here still, you know, so again, it's us about learning things. It's not about guessing something crazy by looking at two examples. It's about learning more about the problem. Okay, so what seemed to have messed up our original guess is these numbers here. Okay, if you give me this pattern 3, 6, 9, 12, and you tell me, hey, what do you see going on in here? I see, oh, multiples of 3, right? Probably a lot of people will see that. So it looks like multiples of 3 messed up what we were thinking. Well, so how about we ignore these multiples of 3, so maybe we look at only at multiples of 5 in here. Well, so if we were to look at multiples of 5, numbers relatively prime with 5, not with 15, but with 5 only, well, it would be 1, 2, 3, 4, so this would be okay. Now this would also be okay, this would also be okay, this would also be okay. Okay, so now we would have a pattern in here, right? We would have the same behavior in between 1 and 5 as we have in between 6 and 10, as we have in between 11 and 15. Again, not by looking at numbers that are relatively prime with 15, but only with 5. Okay, maybe if we go back to this previous example, okay, so now let's say we only look at numbers that are relatively prime with 6. Well, 2, 3, and 4 are relatively prime with 6. Are not relatively prime with 6. 8, 9, and 10 are not relatively prime with 6. 14, 15, and 16 are not relatively prime with 6. So this previous pattern will have no change at all. Okay, so now in this case, we kind of see that again, by relaxing a little bit the search that we have in place, we see that what happens in this interval here is exactly what happens in this interval here, is exactly what happens in this, actually not intervals, but set of numbers. And the same would be true now with this relaxed sort of condition with numbers from 1 to 5, respectively numbers from 6 to 10, and numbers from 11 to 15. All right, so now maybe, okay, can we maybe look at some kind of claim? All right, let's say if we look at numbers from 1 to all the way up to n, all right, and numbers from n plus 1, n plus 2, all the way up to 2n, okay, and numbers from 2n plus 1, 2n plus 2, all the way up to 3n, okay. So if we look at these groups of numbers, will we see patterns among these groups when we try to figure out numbers that are relatively prime with n. So we are going to have here 5n many. Okay, are we going to have here 5n many? I don't know. Are we going to have here 5n many? Okay, maybe yes, maybe no, but maybe it's worth looking into this kind of situation. Now, if this is true, well, are they distributed nicely? Again, I don't know, but something to look into. Okay, and we are going to look into that in the next video.